Hello students, welcome to Marine Engineering Tutorials. I'm Atul Kumar Gupta and I'm back with a new tutorial. Presently we are studying marine auxiliary systems. In this lecture, we will first learn about the role of pumps in pumping systems. Next, we will explore the type of pumps. Then we will study the losses of head in pumping systems. After that, we will discuss the Reynolds number and the type of flows. Next, we will study Moody's diagram and find absolute roughness for some of the pipe materials. Then we will learn about the effect of temperature on liquids, vapor pressure, and its effect on suction lift of the pump. Finally, we will study the power required to pump the liquid. Let us now go through each of these topics one by one in the following slides. Role of pumps in pumping systems. What is the purpose of a pump? For the operation of a ship, various liquids are required to be circulated through different systems. The job of movement of these liquids are performed by pumps. How the liquids are moved by the pump? Pumps impart energy to the liquids being transferred by mechanical means using moving parts. Thus, a pump is a device which creates the flow of liquids, and in doing so, the pump has to overcome the resistance offered by the system. The flow is achieved by creating a pressure difference in the system. How much pressure is generated by the pump? Generation of pressure is dependent on the resistance to be overcome. Within the system, power required by the pump is dependent both on the flow and the pressure to be raised. What is the role of a pump in a piping system? Pump divides the piping system in two parts, namely suction and delivery sides, and each side has its own characteristics. How the liquid enters in a pump. The liquid must flow to the pump on its own, either due to the head of a tank or due to head caused by the atmospheric pressure acting on the suction side of the pump. What is the maximum suction or delivery lift of a pump? The suction lift of a pump is restricted theoretically by the head caused by atmospheric pressure, which in practice is reduced by losses of heads in the suction pipe. However, there is no restriction of lift on the delivery side, although losses do occur in this side too. The pump has to overcome all the losses both in suction and delivery sides, and in addition has to create the necessary head to lift the liquid, otherwise the pump stalls. Types of pumps. Pumps can be broadly classified in two categories. Rotodynamic pumps. Rotodynamic pumps provide a continuous flow and their delivery pressure remains steady over time. Centrifugal pump. Centrifugal pumps fall into this category. They are suitable for handling low viscosity liquids and are commonly used where high flow rates at low heads are required, such as water and low viscosity oils. Their pumping action. Pumping action is achieved by creating suction and reducing the liquid into the pump, after which the impeller imparts centrifugal force to the liquid, propelling it outward. There are limitations. Since these pumps cannot handle vapors, they are often equipped with a pump priming arrangement to remove air or vapors from the suction side. This is particularly necessary when the pump is expected to lift liquid from a level below its position, especially in the case of volatile liquids with high vapor pressure. Positive displacement pumps. These pumps are self-priming and are capable of creating a high vacuum, making them suitable for handling viscous fluids and vapors. They are suitable for low to moderate flow rates but can deliver very high heads. Pumping action is achieved by mechanically varying the chamber volume, thereby displacing the liquid from the suction side to the discharge side. Although the pressure developed by the pump is primarily to overcome the resistance offered by the system, these pumps can theoretically produce infinite pressure. Therefore, they are protected by a relief valve against excessive pressure. The output of these pumps is directly proportional to speed, but it decreases with increasing pressure due to internal leakage. This leakage becomes more significant when handling low viscosity liquids. Positive displacement pumps used on ships are broadly classified into three categories depending on the way they displace liquids. Reciprocating pumps. Liquid is displaced by a piston, plunger, or diaphragm moving back and forth inside a cylinder. They may be single or double acting. They are used to handle oil or build water. Rotary pumps. These pumps operate by rotating elements to create a continuous flow. They are further classified into gear, screw, vane, and variable delivery pumps. Gear pump. Gear pumps may use internal or external gears and are generally employed for transferring fuel and lubricating oil. Screw pump. Screw pumps may be single screw, twin screw, or triple screw, providing smooth, pulsation-free flow and are used for transferring fuel oil, lubricating oil, and hydraulic oil. Vane pump. Vane pumps utilize sliding vanes mounted in a rotor that make contact with the stator. They are used in hydraulic power packs and for handling sludge. Variable delivery pump. Axial piston type variable delivery pumps belong to this category in which piston block rotates around the axis while the plungers reciprocate within the cylinder to produce the pumping action. This type of pump is widely used in hydraulic applications. Losses of head in a pumping system. Loss of head in the pumping system is caused due to friction. The friction can be either between the layers of the liquid itself, which is called the viscosity, or between the liquid layer and the surrounding pipe wall. Components of head loss. Head loss can be split in two components. Those are major head loss and minor head loss. Major head loss, HL major, is proportional to length of the pipeline L. It is inversely proportional to the diameter of the pipeline D and is directly proportional to kinetic energy or velocity head, which is equal to V square by 2G. Thus, HL major is equal to F into L by D into V square by 2G, where F is the frictional factor which depends on nature of flow, whether laminar or turbulent, given by Reynolds number Re. Minor head loss is caused by various fittings in the system such as bends, enlargements, reducers, valves, T-junctions, filters, etc. Minor head loss HL minor is equal to kV square by 2G, where K is the loss coefficient usually found experimentally, which varies with flow conditions such as geometry of component, Reynolds number for the flow, and proximity with other fittings. Comparison of K values for some of the common 2-inch fittings are given below. Globe valve has value 6.5 for full open. Foot valve has its value 1.5. Gate valve has its K value of 0.2 when it is full open, 5.6 when it is half open, and 24 when it is quarter open. Butterfly valve has K value of 0.9 when full open, 10 when 2/3 open, 200 when it is 1/3 open. This is the reason why a gate or butterfly valve is always equipped on the suction side of the pump, and it should never be operated with throttled suction valve. 90-degree elbow has value 0.9, 45-degree elbow has value 0.4, and T has value of 1.8. Total head loss HL is equal to sigma HL major plus sigma HL minor. In order to reduce head loss in the suction pipe, short length of large diameter pipe is preferred with minimum fittings. Reynolds number and types of flows. Flow of liquid in pipe can be laminar or turbulent, which is distinguished by the Reynolds number. Reynolds number is the ratio of inertial force to viscous force within a fluid which is subjected to relative internal movement due to different fluid velocities. Mathematically, Reynolds number Re is equal to rho V d by mu, where rho is the density of the fluid, V is the average velocity, d is the pipe diameter, and mu is the viscosity of fluid. Viscosity plays a vital role in pumping operations. It is defined as the internal frictional force between adjacent layers of liquid in motion. Viscous force is proportional to velocity gradient, that is dV by dz. Viscous force is also proportional to surface area A. Viscous force F is equal to minus mu into A into dV by dz, where mu is the coefficient of viscosity. The viscosity of liquid varies widely. For example, water has low viscosity of about 1 cst at 20 degrees Celsius. Heavy fuel oil is highly viscous, whose viscosity may be as high as 380 cst at 50 degrees Celsius. Viscosity decreases inversely with temperature. The value of Reynolds number Re is less than 2000 for laminar flow and greater than 2000 for turbulent flow. Frictional factor F is equal to 64 by Re for laminar flow. However, there is no direct relationship for turbulent flow, which usually takes place in most of the cases and is obtained by Moody's diagram as explained below. Moody's diagram. Moody's diagram is an experimental representation between friction F on the ordinate and Reynolds number Re on the abscissa. Absolute roughness of pipe epsilon by d is also shown on the ordinate. For laminar flow, the relationship is represented by a straight line satisfying the formula F is equal to 64 by Re. Dotted line shows fully turbulent flow beyond which the frictional factor does not change. For turbulent flow, various curves are plotted depending on roughness on the pipe surface. There is a small transition range where frictional factor can be approximately worked out from the two ranges. Absolute roughness of some pipe materials are given below. Galvanized iron or cast iron pipes have the roughness equal to 0.0005. Steel pipes have roughness equal to 0.00015 and metallic and plastic tubes have roughness equal to 0.000005. Relationship between suction lift and temperature or vapor pressure for water. When a liquid is heated, it begins to boil and vapors produced exert pressure on the surface of the liquid. Vapor pressure is defined as the pressure exerted by the vapors when they are in equilibrium with the liquid phase at a given temperature. Vapor pressure depends on both the nature of the liquid and its temperature. As temperature increases, the kinetic energy of the molecules increases, leading to a rise in vapor pressure. Although water has relatively low vapor pressure, an increase in its temperature can still adversely affect pumping performance as illustrated in this table. At 25 degrees Celsius, water has vapor pressure of 3.17 kilopascal and the pump has suction lift of 7.5 meters. At 64 degrees Celsius, water has vapor pressure of 23.91 kilopascal and the pump has suction lift of 3 meters. At 77 degrees Celsius, water has vapor pressure of 48.89 kilopascal and the pump has suction lift of 2.1 meters. At 94 degrees Celsius, water has vapor pressure of 81.4 kilopascal and the pump has no suction lift. At 110 degrees Celsius, water has vapor pressure of 143.38 kilopascal and the pump requires a suction head of 3 meters to lift the water. Similarly, at 123 degrees Celsius, water has vapor pressure of 221 kilopascal and the pump requires a suction head of 6.7 meters to lift the water. We can observe that with increase in temperature of a liquid, its vapor pressure increases which reduces the suction lift. Thus, the temperature of liquid should be maintained as low as possible for its better pumpability. Power required to pump the liquid. This sketch shows a pumping system where a pump takes suction from a tank and delivers the liquid to another tank at a height. Power required by the pump can be calculated from the formula Pa is equal to Q into H total into W by K, where Pa is power absorbed in kilowatt, Q is quantity delivered in liter per second, H total is the total head in meters, W density of the liquid in gram per milliliter, and K has a value 102. H total is the head loss on suction and delivery side, which can be determined from the pumping system. HPRS is the pressure head acting on the liquid surface at the suction. In the absence of tank pressure, atmospheric pressure pushes the liquid to reach the pump suction. H suction is the vertical distance of liquid surface from the pump I. This can be positive when the liquid is above the pump and negative when it is below. HFS is the loss of head on suction due to frictional resistance. HVS is the loss of head on suction side due to velocity. HVAR is loss of head due to vapor pressure. HPRD is the pressure head acting on the liquid surface at the discharge. H delivery is the vertical head of liquid surface from the pump I. HFD is the loss of head on delivery due to frictional resistance. HVD is the loss of head on delivery due to velocity. H total is equal to HFS plus HVS plus HVAP plus minus H suction plus HFD plus HVD plus H delivery plus HPRD. Net positive suction head available is called NPSHA is equal to H PRS plus minus H suction minus HVS minus H VAP. Net positive suction head available should be greater than net positive suction head required. For a pump to operate satisfactorily, NPSHA must always be greater than NPSH required. Otherwise, pump will experience cavitation. NPSHA is calculated from suction piping details, whereas NPSHR is provided by the manufacturer. Therefore, it is the responsibility of the installation engineer to ensure that under all operating conditions, NPSH available remains greater than NPSH required. This completes our basic study about pumps and pumping systems. This book has been written by me and covers all the topics as per Indian Maritime University syllabus. It explains key concepts using simple illustrations. The book also includes answers to all questions that have appeared in examinations conducted by Indian Maritime University. I am sure that the book will help students prepare effectively for exams and also support them in working safely with marine auxiliary systems. I hope you enjoyed the lecture. Feel free to share your feedback in the comment section. If you found the tutorial helpful, consider sharing it with your friends. Subscribe to the channel to stay updated with the upcoming tutorials. I'll be back soon with a new lecture. Thank you for watching till the end.